Alright guys, so welcome to part 2 of your sound notes. In part 1, if you didn't check that out, please do that now. But in that part we talked about some basic sound wave sort of stuff, but also how the frequency of a sound affects what we hear. So now we're going to talk about just kind of some ways in which waves interact with each other in the environment. The first one's kind of an interesting phenomenon. It's called the Doppler effect, and this happens when a device or an object is producing a sound wave, and they produce the same um, frequency of sound over and over and over again. But if that vehicle or that object is moving toward you, like a fire truck or a police car or an ambulance driving down the street, as the vehicle approaches you, you hear it with a higher frequency than after it passes by. After it passes by, you get a lower frequency sound. This, I think, people often hear this with like motorcycles, where and not only does it get louder, it gets louder because as it gets closer because the wave is losing less energy, but the pitch gets higher is higher as it's approaching you, and then gets lower as it passes by. It's kind of an interesting phenomenon. Again, that's called the Doppler effect. Now, some other things that happen here with that are important to know about sound waves are how loud or how soft a sound is, and we perceive this as this is called loudness. How loud or how soft a sound is called loudness, and it's based on the amplitude of the wave. So the greater the amplitude, the more energy, and the more energy, the louder a sound is. Now, this is shown as a transverse wave. We know that sound waves are not transverse. Sound waves are mechanical, and sound waves are longitudinal. They are not electromagnetic. They are not transverse. But because it's often very difficult to visually see what's happening with a longitudinal wave, we frequently use these devices called oscilloscopes that take in pressure waves or compression waves and display them as if they were a transverse wave so that we can better see what's happening. In particular, so we can better see the amplitude. So if we're looking at like these, there's three waves here. The blue wave has the greatest amplitude. That would be the equivalent of having the loudest sound. The green wave would be in the middle, and the red wave would have the lowest volume, or the least loud sound. But if you look, they all have the same number of crests and troughs, so they have the same frequency. So the pitch of these three waves would all be the same. They would just be a different loudness. The blue one being the loudest of the three. So how loud is too loud is really an interesting question to have. So um, sounds come in all sorts of different loudnesses, and some are really can become pretty uncomfortable or can become damaging to your hearing. So just a normal conversation that you might have with your parents or a brother, sister, or a friend is probably right around the vicinity of about 60 decibels. That's like a normal conversational volume. Decibel is the unit we use to measure how loud or how soft the sound is. Now, if you start to increase how loud sounds are, and you get to like the sound of a hair dryer is about 90 decibels. Going to a concert, that would be about 105 decibels. A chainsaw operating about 110 decibels. If you have an iPod with the volume turned all the way up with the earbuds in your ear, you're looking at about 115 decibels. If you can get louder still, things like jackhammers or the sound of a gun going off or a firework going off if you're near it, these are at or beyond what we call the threshold for pain, which is 120 decibels. It's essentially at that level of loudness that the sound waves become physically uncomfortable to hear, and exposure to them, even in short amounts, can be damaging. Uh, Other sounds that are down here in the 105, 110 decibel range, those things can cause damage to your hearing over longer durations of time. But once you get to the 120 decibel and up range, not only does it become physically uncomfortable, but it can cause damage in just a short period of time. So if we were just going to compare some waves here, these top two waves, we wanted to know which one would be louder. Well, louder means a greater amplitude, so the wave here on the right-hand side has a greater amplitude, and therefore would be a louder sound. We're going to compare these ones at the bottom. They both have the same loudness because their amplitude is the same, but this one here on the left has a much higher frequency, and therefore would be a higher pitch. So you would perceive that as a higher sound. You would perceive the one on the right here as a lower sound. Now, sound, when that bounces off of a surface, just like any other wave, we call it reflection, but we have a special name we use for sound, and we call it an echo. And there are different animals or even technologies that use an echo to help locate things. This works especially well in areas that are darker, whether it's an animal like a bat that hunts at night, and so it's dark in the environment, or a dolphin or a submarine that might be pretty deep below the water where there's not a lot of light to be seen. So in these situations, sound waves are sent out. They bounce off the surface of whatever object is in their way, and that sound wave then comes back as an echo. And with that information, the animal or the submarine can tell how far away an object is. And depending on how the amount of time it takes for those waves to come back changes, you can know whether you're getting closer or further away from that object. And how many of those waves come back tell us about the size of the object and the shape of the object. So this process is called echolocation. But we have a unique name for it when it's being used by human-made ships. Navigators that use this technology, it's referred to as sonar. It's a lot like radar, which we talked about with light waves, but instead of using light waves, it uses sound waves to do this. It makes it great to use in dense medium, or a medium where there's not a lot of light, like looking for fish deep in the water. This would be a good place for a good way for a fishing boat to know where to stop and cast out their nets. In medical profession, we use the same sort of technology in what's called an ultrasound. These use sound waves that are higher frequencies than what we can hear, and they send those high frequency waves into the human body, that they hit off certain things and bounce back. And this lets us see kind of an image of what's happening inside of the body. It's a lot like an X-ray, but instead of using radio waves, or instead of using electromagnetic waves like X-rays, it uses sound waves to do this. So that's that whole process is called ultrasonography, or you would go and get an ultrasound done. Interference with waves occurs when waves overlap. In sound waves, this happens kind of in two major ways. You have constructive and destructive interference that both can happen. There's also resonance, which we'll talk about in a moment. But in constructive interference, so you have like the crest of one wave that overlaps with the crest of another wave, and the trough of one wave overlaps with the trough of another wave. So when these two waves get combined, the two crests build a taller crest, and the two troughs dig a deeper trough. So you end up with a greater amplitude. This results in a louder physical sound. The waves have greater amplitude, and that is perceived as a louder sound. On the other hand, if you have the same frequencies, but they're at slightly different times, you're going to have destructive interference, where this wave's crest overlaps with this wave's trough, and this wave's trough overlaps with this wave's crest. And the result is that the amplitude decreases. And if this is done perfectly, you can actually completely eliminate the movement of the medium, and therefore make it silent. So, but even if it's not perfect, you can decrease how loud a sound is. So this will allow you to produce softer sounds, or if done perfectly, total silence. Resonance is the vibration of an object, typically at its maximum amplitude, and this happens often when one object is vibrating near another object. It causes that second object to begin to vibrate. So that's resonance, and that's, we kind of saw a video with this earlier, where you can make a glass shatter if you produce things at the right volume. This is also what caused the Tacoma Narrows Bridge to collapse, is resonance. Now, sometimes when a lot of noises are being made and there are a random mix of different sounds that are undesirable, it's referred to as being noise. Like there's a lot of noise in the cafeteria during 8th grade lunch because it's a lot of sounds that are generally undesirable and a pretty random mix. So that's what we would call noise. So in science, when we use the word noise, that's what we're referring to. Diffraction of sound produces is kind of really important for us, and it's kind of visually represented in these two pictures, where there's a radio on one side of a wall, and then around a bend is a person standing. But the person standing around the bend can hear the sound, and the reason for this is because of diffraction, the bending of a wave around a barrier or through an opening. So in this case, kind of an overhead look here is this is the person, and then this is the radio, and the radio emits its sound out, but the waves that come out this way bend around the wall, so the person over here can hear those, and that's why we can, hear teachers that are in other classrooms if we leave our classroom door open, or we can hear kids that are in the locker area if our door is left open to our classroom. It really lets those sound waves really let us hear things that we can't see or things that are not in a direct line to us. Because sound waves often have really long wavelengths, they diffract quite a lot. So we really can hear a lot of what's going on around us, even if we don't have a direct straight line to the object producing the sound. The last couple things are not on the notes, but I think it's kind of worth knowing. And this is the first thing to talk about is what we call the sound barrier. So as things begin to move and produce sound, and they get closer and closer and closer to the speed of sound, they form these compressions, but the compressions of all those air particles build up and get more and more and more and more and more dense as the object moves, and it creates a really, really dense wall of air in front of the vehicle, like the plane, for instance. And that wall is referred to as the sound barrier. Now, we can push through that, but when that happens, you get what we call a sonic boom. It's a really loud sound. That's what happens when we break the sound barrier. The sound barrier. And kind of an interesting thing that happens physically when this occurs is it creates a really low pressure zone behind the object that's pushed through the sound barrier, and so it also ends up producing a cloud because of that change in temperature due to a change in pressure. And then that sound gets sent out in what we call a shock wave. So that's kind of something interesting to know about as we approach the sound barrier, because we can travel faster than the speed of sound at this point. So hopefully that all works for you, makes sense. If you have any questions, make sure you let me know. You can shoot me an email or stop in and see me. Have a great day, guys.